We're asked to find the minimum takeoff velocity for an aircraft, which we've been given the variation of the lift coefficient versus angle of attack, and we're also told the weight of the aircraft, 650,000 pounds, the reference area, and we're told that the airplane is going to take off at sea level, where the density is about 2.4 times 10 to the minus 3 slugs per cubic foot. Okay, to solve this problem, we'll connect the velocity to the performance of the aircraft, the CL, and all these other parameters through the lift coefficient definition, which we know the CL is the lift over 1/2 rho V infinity squared S ref. So we can rearrange that to solve for the velocity. We get V infinity is equal to the square root of 2 times the lift over rho infinity S ref CL. Now, in the takeoff condition, we're going to have the lift is equal to the weight. The airplane is about to come off the ground, but it's not rapidly accelerating. It's a fairly smooth variation, so that we'll approximate the lift as being equal to the weight at takeoff. And so the takeoff velocity will be the square root of 2 times the weight over rho infinity S ref and CL. And CL then, for a given CL, we can find the takeoff velocity. Now we see that CL comes in as 1 over the CL with a square root, so that as we increase CL, we'll be decreasing the takeoff velocity. And we're interested in the minimum takeoff velocity, so that means the minimum takeoff velocity will occur when we maximize the lift coefficient. Okay, so now we can go back up to our plot here, and we can identify what CL max is for this aircraft, and you can see that it's about 2.5. So to find the takeoff velocity, we now just need to plug in all of the parameters we're given with the CL max that we've identified, and we can find the minimum takeoff velocity. So let's do that a little bit carefully. You can see I've started here. I've got my factor of 2. I have the weight. Here's the density, S ref, and CL. I'm doing this carefully because I want to just make sure we check the units here, and all that's under the square root. So the units of the pound are equivalent to slugs feet per second squared, right? It's a mass times an acceleration. Slug is a unit for measuring mass. Okay, so when you plug that in to this expression, what you see is that the slugs feet per second cubed, the slugs will cancel. What I have here is a 1 over a foot, so that brings an extra power of foot up top, so that's going to be feet squared over second squared will be all that's left. And when I take the square root, I'll get feet per second. So doing that and just evaluating all the math, you should find that the minimum takeoff speed is 217 feet per second. And then you can convert that to miles per hour, and you should find that it's 148 miles per hour. Okay, the other part of the question asks what happens if the airplane were to take off at 5,000 feet of altitude. And the thing to realize there is that at 5,000 feet the density is going to be different. In fact, the density drops to about 2 times 10 to the minus 3. So it's about a 20% drop in the density. And if we look over here at this relationship for the minimum takeoff velocity, when the density decreases, then the takeoff velocity is going to have to increase. And so the conclusion here is that as rho decreases, takeoff minimum speed is going to have to increase. And basically what's happening is, since the density is smaller, we need to get to a higher velocity to create the same amount of lift. Okay, so that's the answer here. Takeoff velocity is going to have to increase if we increase our altitude at takeoff to 5,000 feet.